this video on estimating a population proportion. By the end of this video, you should be able to state and check the random condition, the 10% condition, and the large count condition for constructing a confidence interval for a population proportion. And you should also be able to determine the critical value for calculating a C% confidence interval for a population proportion using a table or technology. All right, so what we have for today is which way will the Hershey Kiss land? So if we took a bunch of Hershey Kisses and kind of rolled them in our hands like dice and dropped them onto the table, are they going to land flat up like what they're supposed to or on their side? Okay, so I did this. I did this in sets of 5, but I rolled these sets of 5 Hershey Kisses for a total of 50 Hershey Kisses being rolled, and I got a sample percentage of 21 out of my 50 Hershey Kisses landed flat, or about 42% of them. Okay, that's our point estimate. So let's see about identifying our population and our parameter and everything. So our population is all Hershey Kisses. Our sample was 50 Hershey Kisses. Our statistic is what we got from our sample. So our p-hat was 0.42. And we never know the parameter here. That's kind of the whole point of what we're doing, but we want to define it, what we're actually looking for. Our parameter is the true proportion of Hershey Kisses that land flat. Okay, so that's what we're trying to infer back to. So let's see here. We're going to go through a few of these things. Was this sample a random sample? And why would that be important? So it says each of 4 groups selects a random sample. So yes, we randomly selected 50 Hershey Kisses. We randomly selected 50 Hershey Kisses. Why would that be important? We got to think back. If you have random selection, then we can generalize back to the population. Okay, that's what we're trying to do here. We're trying to see if we know the population proportion of Hershey Kisses that land on their base. All right, so what is the formula for calculating the standard deviation of the sampling distribution of p-hat? Okay, so we had that in the last unit. This is for one sample, so we're taking one sample. So the standard deviation for the sampling distribution of p-hat is going to be big square root the probability of success times the probability of failure divided by the sample size. All right, let's keep going. What condition must be met to use this formula? So we've said it multiple times, but we're going to we have to put this together now. Your 10% condition must be met to use this formula. So the 10% condition must be met to use the standard deviation formula. Otherwise, you have to use a different formula. Okay. So our sample size was 50, and 50 is definitely less than 1/10 of all Hershey Kisses. Okay. So we met this condition, so we're allowed to use that formula. So we're good there. Okay. Now, We don't know the value of p, so we just wrote this formula using the population proportion. We don't know that. We have no idea what that is. That's what we're trying to do. So what we need to do is we're going to use p hat instead, because that's a number that we actually have. Okay? So we're going to say the standard deviation of p hat equals, well, our sample proportion was 0.42. That's my success, so failure would be 0.58. And we had a sample size of 50 Hershey Kisses. And when I calculated that out, I got 0.0698. Okay. So now, would it be appropriate to use a normal distribution to model the sampling distribution of p hat? And we need to justify our answers. When we're talking proportions, we're talking large counts. If we were talking means, that would be central limit theorem. But when we're talking proportions, this is large counts. So normally we would do n times p has to be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10. But we don't have p, remember? That's what we're trying to infer back to, but we have p hat. Okay, so we're going to use p hat to calculate this. So our sample size was 50. Probability of success was 0.42. So that is 21, which is in fact greater than or equal to 10, so we're good there. Sample size 50 times 0.58, and I got a 29 there, which is also greater than or equal to 10. Because these are both greater than or equal to 10, that means the shape of the distribution is approximately normal. So we can use the normal calculations to determine some probabilities. All right, so we did a bunch of stuff here, and it's really a lot of stuff that we've been doing along the way, but let's take a look. As we start to do these questions now, we need to make sure certain conditions are met in order to continue moving forward. So the first thing that we need to check is randomness, because if we're going to infer back to the population, we must have a random sample. So this is condition 1. And we're going to have to check this each time now. If we don't have a random sample, we've got a little bit of a problem here. Okay? So in order to be able to use our standard deviation to use it, the 10% condition must be met. So this is our second condition that we need to always check. Okay? So we have to check if it's randomly selected so we can generalize. We have to check the 10% that so this is really talking about the independence. We're not taking too big of a sample, so we can use this standard deviation formula. And then the last thing we need to do is we need to make sure that our distribution is approximately normal, because if we're going to do that, if it's not normal, we can't perform z-scores calculations on it. So this is the third condition that must always be checked. Condition 3. Okay? So all three of these are going to have to be checked each time we're trying to do these problems. Now, there's one other little thing I want to address here, is this was the formula that we've been working with, but we do not have the population proportion, so we just used the sample proportion because that's what we've got. We don't really have a choice. So that's really no longer called standard deviation. It's the same formula, but where the number came from was from a statistic. So when it's like that, we call it the standard error. It's still the standard deviation, but its more official name is standard error of p hat in this case. Okay, and so instead of the sigma of p hat, we're going to say SE for standard error with the little p hat there. Okay. So it's not really, it doesn't change the formula, it doesn't change how you plug anything in. It's just a notation issue that we want to say it's the standard error of p hat, which is the square root of p hat times 1 minus p hat divided by n. Okay? So it's just it's one of those things that we want to make sure that we're calling things what they actually are. All right. So the other day, we constructed confidence intervals, okay? So now we're going to start to formalize this sum. All right, so let's flip this over and take a look at the backside. So when we have a confidence level, it's telling us really how many standard deviations out from the mean. So in a normal distribution, 95% of the data lies within 2 standard deviations from the mean. You remember that from our empirical rule. So this value is called the critical value. Okay, the 2 standard deviations away from the mean. So a critical value, and so this is going to be part of us determining how to calculate our margin of error. So what I have here is these numbers are confidence levels, 80%, 90%, 95%, 99%. These are actually confidence levels. And these are the most common of the confidence levels that you're going to run into. So remember, a confidence level is if we took many, many, many samples. So if we're talking about we're 80% confidence, if we took many, many, many samples and performed, got a confidence interval on each of them, about 80% of the confidence interval would capture the true population, whatever it is that we were talking about. Okay, so these critical values are going to be part of the formula for our margin of error. So I want you to envision this. We have our normal curve, okay? I want 80% of the data from the middle, because this is really our confidence interval. My point estimate would be right there in the middle, and then my margin of error would come out side to side, okay? If 80% is in the middle, that means I have 10% of the information over here and 10% of the information over here, so it adds up to 100%. The critical value is what is this standard deviation line, okay? So if we got out table A, we could look up this percentile number to get the z-score for here, and it's going to be mirrored over here because this is symmetrical. Okay, so here's what we're looking at. So 10% would be 0.1. I want the closest value to 0.1. Let's see, so I have 0.1003 right here. It might be a little hard to see. And that z-score for 0.103 is negative 1.28. Okay, so this would be negative 1.28. And so with symmetry, this line on the side would be positive 1.28. So the critical value, when 80% of the data lies within how many standard deviations of the mean, it's within 1.28 standard deviations from the mean, below or above. Okay, so I'm going to recommend that you memorize some of these numbers, particularly the 90 and the 95%, because you're going to use them all the time. But I want you to also understand where the numbers came from, because they could ask you an oddball number and you have to go look it up. You got to figure it out yourself. So 90% of the data is how many standard deviations from the mean. So 90% of the data, we're talking about the 90% in the middle, which means there's 10% left over for either side symmetrically, so we've got 5% on each side. Okay, so that's an area of 0.05 when I convert it out. So to get to the closest I can get to 0.05 is, let's see, here, and it's really exactly between these two numbers, negative 1.64 and negative 1.65. We've talked about that before. When it's exactly in the middle, you can use the very in between of a half to go in there. So that'd be 1.645 standard deviations, because this would be negative 1.645, and this one will be positive 1.645. Okay, so this is where these numbers are coming from. We want within the standard deviations from the mean. So we're talking about the middle part, the confidence interval. This would be our point estimate, and then that would be our margin of error going out both directions. So I don't want to keep calculating this each time, but I want you to understand this is where the numbers came from. I'm looking up this percentile number and getting the z-score from it. So if you're going to be 80% of the data lies within 1.28 standard deviations but from the mean, 90% of the data lies between 1.645 standard deviations of the mean, 95% of the data lies, now when we use the empirical rule, it was 2, within 2 standard deviations from the mean, but really what we want to use for our critical value here is the number 1.96. Okay. 95% of the data lies within 1.96 standard deviations from the mean, and 99% of the data lies within 2.576 standard deviations from the means. So these are numbers, these 4 in particular, you really want to remember. They get used a lot, and really these 3 right here are the ones that get used the absolute most. Okay. Remember, on a confidence interval, the more confident you are, the wider your interval is, and the bigger your margin of error. So you try to narrow it some to give you a little bit more information, and 95% is the one you kind of see all the time. And if you think about it, that 95% relates really closely to that 5% number that we've talked about, that is it statistically significant or not. And well, yes, if it's less than 5%, we're saying it is. Here it is again. This is just showing you the other side of it, okay, the between part instead of the outside edges part. All right, so we're going to calculate a margin of error for a 95% confidence interval by multiplying the critical value in the standard deviation we found on the front, okay? So a 95% confidence interval has this critical value of 1.96, okay? The standard deviation that we found on the front was 0.0698. When I multiply these together, instead of us making up that margin of error like we did the other day, this will tell us what the actual margin of error is. I got 0.137. Okay, so this is our margin of error. Now, to make the interval, we're going to take that point estimate and add and subtract the margin of error, just like we did the other day. So our sample statistic was 0.42. Okay, and we calculated this margin of error. So we're going to add and subtract the 0.137, and it's going to give us an interval. And so the interval is often written like this, in parentheses, 0.283. 2.557. So what I'm saying is all the plausible values for the population parameter would be between these two numbers. Okay, so in this case, the plausible values for the proportion of Hershey Kisses that land flat on their bases are between these two proportions. Okay? All right, so before we move on, I want to kind of go back and look at some of this. So these critical values, we call them Z-star, okay? These are all Z-stars. All right, now the formula to find your margin of error. So your margin of error equals your critical value times the standard error. Remember, the standard error is the standard deviation, but we call it standard error because the number came from a statistic and not a parameter that we plugged in. Okay, this is how it looks in words. In symbology, our critical value is Z star, and our standard error we wrote as SE, and we're talking about proportions there. Okay, so that's what we've done. This is Z star, and this is the standard error of p hat. Now, that's how you get the margin of error. To get the actual interval, you need to take your point estimate and add and subtract your margin of error. Okay? And so what that looks like in symbology, in this case, this is a proportion, so we represent it with p hat. And we added or subtracted. I'm going to go ahead and put how we got our margin of error, which is Z star times the standard error of the sampling distribution of the proportion. Okay. And so the full thing, p hat plus or minus Z star times square root of p hat times 1 minus p hat divided by n. So this is a formula for the sampling for a confidence interval. So this is a confidence interval for a proportion. And of course, means is different because how you get means standard deviation is a completely different formula. So we'll be talking about that later. Okay, so to create our confidence intervals, you would take a sample. From the sample, that's where this comes. From the sample, you have to create a margin of error that you're going to add and subtract out. This is how we get our margin of error to get these wings that go out to tell us the plausible values we think the true population proportion in this case falls into. Okay, so here I have 13 trials of 50 Hershey Kisses, and I'm showing you the proportions of them that land flat. Okay, so we have our confidence interval. The points in the center, that's the actual sample statistic, the proportion they got in their sample. And then these whiskers that go out to either side is the margin of error. So their interval would go from this, so what, 0.21 to 0.48 or so, okay? So it's showing you the interval width, and you've got your point estimate in the middle. What I want you to think about is take a second and look at this. Pause the video. What do you think the true proportion of your Hershey Kisses that land flat is? So we have a 95% confidence interval. That means after many, 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 many samples, and if we create a confidence interval on each of them, 95% of those confidence intervals should capture the true population proportion of Hershey Kisses that land flat. I don't have many, many, many samples. I've got 13. So just take a look at it, make an estimate, draw it in, and I come back when you're done. All right, well, hopefully you actually paused the video and tried to make a guess, because looking here, we want 95% of these to kind of run over the same spot to hit a 95% confidence interval. And so somebody has actually collected data on many, 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 many samples of people rolling Hershey Kisses and landing flat on their base. And so the the number that's been released of Hershey Kisses that will land on their base is 35%. So right here at 0.35, let me write this in. This is the true population proportion right there. Okay. So how did we do? We have, it looks like, and I got a little crooked there because this one doesn't actually touch. This guy does not touch, but all the other ones do. So we have 12 out of 13. Let's see, 12 divided by 13 is 92%. Of course, we all know short-term variability, right? Because this is really a long-term, your confidence level is a long-term probability, and this is a short-term run. But we were very close to 95% there. So that's the idea of a confidence interval. Let's flip over and let's formalize some of the stuff that I want to be sure that you take away. All right, the first thing are these conditions. They must be checked each time. Otherwise, we can't do any of these calculations, okay? You have to make sure that they're random and say, how do you know that they're random? Does it say a random sample was taken? The problem will give us some indication, okay? You have to check that because without random, we cannot infer back to the population, and that's the whole purpose of the confidence interval. We also have to check the 10% condition so we can use our standard error formula or standard deviation formula. Remember, you got to make the comparison that your sample size is less than 1/10 of whatever your population is. Okay? You can't just say 10% condition checked. You actually have to show it worked out, showing that you checked it. And the last one is our distribution has to be approximately normal so we can find z-scores and find the area and everything. So you have to check to make sure that the shape is approximately normal. And so you use large counts for proportions, and that's the n times p hat in this case because we don't have p. That's the whole reason we're doing this. And n times 1 minus p hat. All right? So those are going to have to be checked. Our critical values, I have the most important ones here. You really should memorize those just to save yourself some time. That a 90% confidence level has a z-star of 1.645, 95 is 1.96, and 99 is 2.576. To find any percentage, remember you're taking your percentage out of the middle, and so I just look up this lower bound, and you look at the area because you got to find out how much is left over, and then go back, work backwards to get the z-score. Okay. All right, and then the last one is just finding all our formulas all together in one place. So it's to find a confidence interval for proportions, you got to take the point estimate plus or minus your margin of error. Okay, and so that's p hat plus or minus z-star times the standard error for p hat. And it's the standard error p hat because we used a statistic instead of a parameter. All right. Give the Check Your Understanding a try. The answers are on Canvas. Let me know if you have any questions. I'll see you in class.